So this is chapter 2, Tools of a Healthy Diet. So again, just like in chapter 1, we'll always start off with this list of student learning outcomes or objectives. And again, I invite you to read this list. I won't read it to you. Hopefully by the end of this chapter, you can come back to this list and you can remember, everything that we've talked about and how it relates to these learning objectives. That's the goal. Okay. So we're going to start right off with the first part of this chapter, 2.1. And here we're going to talk about the dietary reference intakes. That's how we're going to start, which we use DRIs in short to represent these. There's a tool, Appendix J, that you'll see. It's in the back of our textbook, but I've also put a link to it on our Brightspace course site so that you have easy access to a PDF of that file. And all of these standards that we're going to talk about are in Appendix J. And so you will see there will be a separate video of me going through that appendix just to make sure that you understand what's in there. Okay. So these dietary reference intakes, these DRIs, which again are covered in Appendix J, these are recommendations from the Food and Nutrition Board and the National Academy of Science. These are used for planning and assessing diets. They apply to people in both the US and Canada, so North America, and they have set 5 standards. The first one is called the Estimated Average Requirements, EARs. The second are the RDAs, which are the Recommended Dietary Allowances. Adequate intakes, which are AIs. Tolerable upper intake levels, which we call either upper levels or ULs. And then Estimated Energy Requirements, EERs. Okay. And again, I will show you Appendix J in that other video. We will go through some of those. We'll notice when we get there that the dietary reference intakes, so each of those standards, they're going to differ by life stage. So individuals who are of different ages are going to have different requirements for nutrients. After age 9, there's going to be differences according to biological sex. People who are pregnant or who are lactating, they're going to have different requirements as well. And so those 5 standards are going to be dependent on these things. Okay, so the dietary reference intakes are going to differ by life stages. Okay, and although these are not one of the 5 standards of the DRIs, they actually are covered in Appendix J, so I will touch on them when we get there. We also talked about this briefly back in chapter 1. Acceptable macronutrient distribution ranges, so the AMDRs. They're the established guidance on intake levels for our macronutrients, so carbohydrates, proteins, and fats. These have been developed to help reduce the risk of nutrition-related chronic diseases, and to make sure that we get enough of each macronutrient and not over that amount of macronutrient or under, decreasing the likelihood of obesity and cardiovascular disease. Also malnutrition, undernutrition, not just overnutrition. Okay, where's my pointer? Here we go. Okay, so let's go to the first DRI. Okay, so the first one is the Estimated Average Requirements, or the EARs. These are daily nutrient intake amounts that are established to meet the needs of half, so 50% of people in a certain life stage. And so if we look at this figure down, it actually shows the EAR, the RDA, the AI, and the UL. And it's going to be repeated on multiple slides. So if we just look at the EAR here, and we look at this trend line in purple, this says % of healthy population at risk for inadequacy, so something of a deficiency. And the flip side is the risk of toxicity, right? And so right here, this EAR, you can see it's at the 50% level, right? So this is the percent of a healthy population at risk of inadequacy. So these are numbers that should meet the needs of half of the people in whatever life stage we're talking about. In order to set this standard, the Food and Nutrition Board, they must agree that there is an accurate method to actually take this measurement of whether intake is adequate or not. These are called functional markers. So there has to be a functional marker, a way to evaluate and test something in the body. So for example, an enzyme in the body or the ability of a cell or organ to maintain normal physiological function. If there isn't an available marker, then an EAR cannot be set. So there's going to be some nutrients where there is no EAR. Okay, so again, this states that 50% of a specific life stage, the people in that life stage, would have their needs met if they met that particular amount of whatever nutrient we're talking about. Here's an example. So vitamin C. We know vitamin C is a micronutrient. It's a water-soluble vitamin. It's really important for proper immune system function. Okay, so you need to have it. How much do you need? Okay. And so the amount of vitamin C in white blood cells, these are our immune cells, is going to serve as a functional marker for vitamin C. So that's the measurement that's been taken. It's been shown that 75 milligrams a day for men and 60 milligrams a day for females, adults, is enough vitamin C to saturate white blood cells, which we think is enough. Okay. The EAR for vitamin C has been set to 75 milligrams per day for young men and 60 milligrams a day for young women based on this. Okay. And again, this is the amount that is thought to meet the needs of 50% of the individuals in that life stage. Importantly, EARs are used to evaluate the adequacy of diets or nutrients of groups and not individual people. Okay, here's the next one. So those are EARs. And again, I'm going to show you where those are in Appendix J on the next video. So the next standard, the recommended dietary allowances, or RDAs. Lots of acronyms here. So the RDAs, again, are the second standard for the dietary reference intake, or the second DRI. Okay. These represent daily nutrient intake amounts that are sufficient to meet the needs of nearly all individuals, so 97 to 98% in a certain life stage. So not 50%, but most. Okay, so again, if I come down here to that same exact graph, RDA, recommended dietary allowance, if I come down here, this is, so again, the percent of a healthy population at risk for inadequacy goes way down to, and there's not actual numbers on here, but down to like 2 or 3%. Okay, so there's a huge decrease in the number of individuals that would be at risk for an inadequacy. If I come to, to the other side of this as well, the percent of healthy individuals at risk for toxicity is also, down. Okay. So people are not going to be nutrient deficient. They're not going to be in that range of toxicity either. So again, nearly all individuals in a certain life stage will have sufficient daily nutrient intake to meet their needs. How is this number figured out? You're not going to have to calculate this, but just so that you know, it's based on a multiple of the first standard, the EAR. Here's the equation. So the RDA, so again, recommended dietary allowance, is equal to the EAR times 1.2. Okay, so here's an example. If the vitamin C for the young females is set to 60 milligrams per day, to figure out the RDA for vitamin C for young females, it will be 60 times 1.2, and that's about 75 milligrams per day. So about 75 milligrams per day should meet the needs of 97 to 98% of young females. Okay. And again, this isn't just a willy-nilly number. It's based on science. It's based on the amount of the nutrient's ability to prevent chronic disease, rather than just prevent deficiency. Okay. The next DRI is adequate intakes, or AIs. Okay, so this is the third standard. This is going to be daily intake amounts that are set for nutrients, which there is insufficient research to establish an EAR, and therefore we can't establish an RDA. These are based on observation or experimentally determined estimates of the average nutrient to maintain a defined nutritional status. These amounts should also cover the needs of 97 to 98% of individuals. And some examples of nutrients that have only AIs, not RDAs or EARs, are things like essential fatty acids, some of the B vitamins, fiber, I don't know if you can see that, choline, and fluoride. Okay, the fourth standard are the tolerable upper intake levels, or I usually use ULs for short. And if I come down here to this table again, or graph, you can see again, here's EARs, enough to meet the needs of 50%, RDAs, enough to meet the needs so that only 2 to 3% are deficient. And then we have adequate intakes, and those levels are between RDAs and ULs. So here are the ULs, the upper limits. And you can see here, this is where, 97 to 98%, or on the flip, if we do, less than 3% of healthy population is at risk of toxic adverse effects. So again, this is the maximum daily amount of a nutrient that is not going to cause a deleterious, and adverse health effect for 97 to 98% of individuals. Okay, this applies to chronic daily use. So if you exceed, an upper limit, hopefully not by much, but like once, not a big deal. But if you chronically exceed an upper limit, that's going to be bad. So that it applies to chronic daily use, and it's set up to protect those who are susceptible in the healthy population. It is a ceiling that you should not go above for nutrients. So for example, vitamin C. We talked about vitamin C a little bit. We said that it's important for immune function, right? It has an EAR, it has an RDA, and it has a UL, right? So it is a water-soluble vitamin, but it still has an upper limit of 2,000 milligrams per day for adults. What would happen if you exceeded that limit chronically? You might end up, with diarrhea. Okay, not terrible, but still not enjoyable. On the flip side, exceeding the upper level for vitamin A, for example, which is set at 3,000 micrograms. Notice the difference in units. So for vitamin C, these are milligrams. And for vitamin A, this is microgram. So looks like a U kind of. It's actually not a U, but so micrograms per day. So notice the difference in units. That's going to be important when you look at Appendix J and you see all these different standards and the values for these different nutrients. Make sure you pay attention to units. If you have chronic overconsumption, if you chronically exceed the upper limit for vitamin A, it could be really bad. You could end up with liver damage, headaches, vision problems. It could even lead to coma and death. So again, chronically exceeding the upper limit would be bad. Iron, again, can cause toxicity. So the upper limit for iron is 45 milligrams per day. You don't want to go above that ceiling. If you do, it could lead to gastrointestinal problems. It can lead to organ damage. And again, in very severe circumstances, it could even lead to death. The dose is the poison, right? How much over that limit are you going? Okay. And lastly, our fifth DRI estimated energy requirements. So these are the EERs. Again, lots of little acronyms here. This is estimated energy requirements are the average daily energy needs. So calories, how many calories do you need for each life group? So this is going to include, again, carbohydrates, proteins, fats, and alcohol. All contribute to your total calorie need. It's an estimate because energy needs depend on energy expenditure, and we're all a little bit different, right? How much does it take to keep your body functioning, at homeostasis? How much energy do you need for that just to keep your body functioning there? And then what's your activity level? What are you doing all day? Are you an athlete? You're how much energy you use, that's going to determine how much energy you need to consume. Okay. If you eat below your calorie need, so if you are in a calorie deficiency, that will cause weight loss. If you consume over the amount of calories that you need, that will get stored as body fat and will end up with weight gain. Okay, so it's really about calories in, calories out when we're talking about EER. Okay, you are going to use this chart for now. In later chapters, we'll actually do a calculation, which will give us a better picture. But for now, we're just going to use this table. And so you have to refer to this table a bunch. This is the estimated energy requirements. Okay, and again, we can see age groups here. So children, ages 2 to 3. When we get over the age of 3, we break it up according to gender. So we got females and males, and we've got different life stages. Okay, different ages. And then there's a range of calories, right, depending on your activity level. So if you're sedentary, if you don't do much, versus, how active are you? So there is going to be this range. So again, this is an estimation. So if there was a problem that said, we're doing an analysis on a 14-year-old female who is sedentary, you're going to use this number here. Where's my pointer? You're going to say, okay, she needs 1,800 calories a day. Let's say it was a 22-year-old male. Okay, I come down here to the purple, male. Okay, that's this range, 22, and he's really active. He's an athlete. I'm going to use 3,000. Okay, so again, these are estimates, not perfect science, but they're estimates. Okay, based on age, gender, and activity level. And again, this is not one of the DRIs, the acceptable macronutrient distribution range, AMDRs, but we're going to talk about it here, and we're going to actually do some calculations with it and with EER. Okay, so again, I introduced you to this now twice. Again, it's not a DRI, but it is guidance that is provided and actually is in Appendix J. And so these are ranges. So what this says is that for carbohydrates, 45 to 65% of your total calorie intake should come from carbohydrates. Protein should be 10 to 35, fats 20 to 35. Okay, and these numbers are for adults. It is different for younger individuals. So you need to be in that range, okay, without exceeding 100%. And so again, what are these for? They're established guidance, telling us what our levels should be for these. And it's based on, the percent of energy associated with the reduced risk of nutrition-related chronic diseases like obesity and cardiovascular disease. It's all about prevention. Nutrition for prevention. Okay, so let's try a problem. All right. So the question is, how do these AMDRs, acceptable macronutrient distribution ranges, translate to calories and grams? Okay. So we played with this a little bit back in chapter 1, but let's do it again. And we'll expand upon it here. So it says, how many grams, here's the question, how many grams of carbohydrates per day should a sedentary adult female consume to maintain body weight? Okay, so we've got to use the chart. I'm going to flip back. Okay, so it just says adult, which is tough. Let's use this range here. When I think of adult, I think my age range. But, 18-year-olds are adults too. So usually in these questions, and I don't know why I didn't do it here, I will give you an age. So let's use the 31 to 50 range. Okay, let's say she's a 32-year-old adult female. Actually, let me back up. I didn't do that, right? Yeah, I didn't. Okay, there should be an age in there, and there will be on other things that I give you. So she's an adult and she's sedentary. Okay, so she needs around 1,800 calories per day. Okay, somewhere in there. We're going to use 1,800 as our number. Okay. So we need to know how many carbohydrates per day she needs to maintain body weight. So she doesn't want to lose weight. She doesn't want to gain weight. She wants to stay the same. So again, the first thing we should do is go back to that table and find the EER for an average sedentary adult female. Again, let's say she's 40. Okay. We would find that number, and that's about 1,800 calories per day total. So all of the food from breakfast, lunch, dinner, any snacks should come out to a total of 1,800 calories per day. Okay, so next we've got to figure out what's the AMDR for carbs. And so the range there is 45 to 65% should come from carbohydrates. Okay, so we need that number. We got that. So now we're going to apply this. So how many calories of the 1,800 should come from carbs? And so 45 to 65% of them. And so let's actually get the calories. So how are we going to do that? We're going to take 45%, change that into a decimal, so that's equal to 0.45. And we're going to multiply that by the total number of calories she should consume in a day. So 0.45 times 1,800 equals 810. So on the low end of the range, she should be consuming 810 calories from carbohydrates. And on the high end of the range, 65%, same thing, 0.65 times 1,800 equals 1,170. Okay, again, there'll be problems that you're going to have to work through in your lecture assessment packet and on the quizzes. So, come back and practice this. Watch me, do it again. So there's the range of calories. So about 810 to 1,170 of her calories should come from carbohydrates. Okay, so we know how many calories. Now we got to figure out how many carbohydrates is that. And so remember back to chapter 1, 1 gram of carbohydrate provides 4 calories. And so just divide. Divide the number of calories that should come from carbs by the number of calories in 1 gram of carbohydrate. And so at the low end, again, we said 810 calories divided by 4 calories, because there's 4 calories in a gram. If my math is right, that should be 202.5. So at the low end, 202.5 grams of carbohydrate should be consumed. And at the high end, 1,170 divided by 4. And that's going to be 292.5 grams. So here's the range of grams of carbohydrates that this female should consume in a day to maintain body weight, according to the AMDRs. Somewhere between 202 and 292. Okay, so we went from total calories. We figured out using the AMDR, the range of calories that should come from carbs. And then from that range, we were able to calculate how many grams, the range of grams. Okay. Okay. There's that problem. Let's go back to the DRIs. So again, we went over the 5 standards plus the AMDRs. Okay. So we've got the EAR, the RDA, the AI, the UL, the EER, and the AMDR. Those are our DRIs. Those are going to be what's in Appendix J. So again, these are intended to guide nutrition programs, nutrition labeling, nutrition policies. These guide research. These guide setting nutrition standards and diet planning. So again, here's a quick table showing the use of these. So EAR again stands for estimated average requirements, represents average nutrient needs, used to evaluate groups, not individuals. Again, 50% of individuals will have their needs met by these numbers. RDA, higher, 97 to 98%. These are used to evaluate current intake for specific nutrients. The more an intake strays above or below this value, the greater likelihood a person's going to either have too much or too little of that nutrient. Adequate intake is kind of equivalent to the RDA, right? It's when we don't have an RDA or we don't have an EAR. Again, 97 to 98% of people would get an adequate intake of that nutrient by having the amount set. UL is a ceiling. We don't want to exceed it, right? For nutrients, EER tells us how many calories we should be consuming in a day. And then the AMDR tells us the range of each macronutrient that we should be consuming. So again, this is a nice little graphic just showing, for nutrients, we should be consuming the RDA, the recommended dietary allowance, or the AI, adequate intake. And if we go above, right, we would be getting closer to the upper limit. We got to be careful there because that can cause toxicity and have adverse health effects. If we go below the RDA and AI, we might fall into the insufficient intake range. And if we're chronically below, that can lead to problems. Okay. Okay. So let's put these into use. So again, the DRIs that we just covered, they can be used to determine the nutrient quality, the nutrient density of a food. Okay. And so to do that, we can actually calculate nutrient density for a specific nutrient in a specific food. And again, there's a little bit of math involved here. What we're going to do is we're going to take the amount of whatever nutrient we're trying to look at in this food. Let's say we want to see, is this food protein rich? Okay, we're going to take the amount of a nutrient in a serving of food, and we're going to divide that by however much we're supposed to get daily of that food. So the RDA or the AI, whichever number we have. Okay, and then next, separately, we're going to divide the calories in a serving of food by how many calories we need daily, so by our EER. And we're going to compare those two values. A food will be nutrient dense if it provides a greater contribution to your or my nutrient need than to your calorie need. So if the first number is higher than the second number, then it's a nutrient, it's rich, it's nutrient dense in that particular nutrient. Let me give you an example on the next slide. We're going to go back to vitamin C. We love vitamin C. So you're going to eat an orange and you want to know, is an orange nutrient dense for vitamin C specifically? Okay. Again, let's say it's the same female, right? 32-year-old, or what I say, 40-year-old sedentary female. So we need to get her EER, right, for our second calculation. So her EER is 1,800 calories per day. So we have that number already. Okay, so now let's look at the nutrient density in this orange. So an orange contains, this is something that I looked up, okay, an orange contains 70 milligrams of vitamin C, okay? So one orange is going to give us 70 milligrams of vitamin C. I'm going to use Appendix J to find what her RDA is. Okay, so again, 40-year-old female, or I forget what exactly her age is, but her RDA for vitamin C, let's say, is 75 milligrams per day. Okay, again, using Appendix J, I would get this number. So I'm going to take the amount of the nutrient in the food, so 70, and I'm going to divide it by the RDA or the AI if I don't have an RDA. Okay, so 75 in this case. So 70 divided by 75 times 100 equals 93%. So she is getting 93% of her recommended dietary allowance for vitamin C from this one orange. That's pretty good. Okay. We got to compare it though. So an orange has 65 calories. Okay. And she can consume a total of 1,800 calories a day. So we're going to do the amount of calories in the orange, 65, divided by her total, her EER, which is 1,800. And again, multiply that by 100 so we can get a percent. And that's 3.6. So what does that mean? That means that only 3.6% of her EER, of her daily calories, will come from this food. That's great. It's a very low calorie food and it's very nutrient dense, right? So we'll compare these two numbers. 93 is greater than 3.6, right? So the amount of nutrients, right, coming from this orange for vitamin C, the amount of her daily recommended, right, for vitamin C is much higher than the calories coming from it. And so yes, this is definitely a nutrient dense food for vitamin C specifically. Okay, here's another example. So we're still looking at an orange, and it's still the same woman, so she still has the same calorie need. Her EER is the same. Her estimated energy requirement, EER, is the same. But we're looking at a different nutrient. Okay, we're looking at calcium now, not vitamin C. Okay, so I had to look this up. An orange contains 52 milligrams of calcium. Okay, so again, that's a number that you'd have to find. If it's a food with a nutrition label, it'll be right on there. Fresh produce, the nutrition label doesn't come on an orange. It also depends on the size of the orange, and the weight of the orange. So it's not exact, it's an estimation. So an average size orange contains about 52 milligrams of calcium. Okay, I'm going to use Appendix J to find her RDA, her recommended dietary allowance for calcium. And for her age and gender, it's 1,000 milligrams a day. So that's how much calcium she needs in a day. She's getting 52 milligrams from this orange. So let's see what percentage that is. So 52, the amount of calcium from the orange, divided by 1,000, how much she needs in a day, times 100 to get the percent is 5.2%. So this means that one orange provides her with 5.2% of the RDA. Okay, not very high. An orange contains 65 calories. Okay, that's the same as before. So 65 divided by 1,800 times, divided by 1,800 times 100 is 3.6%. Okay, this means that again, 3.6% of her EER will come from this food. So when we compare 3.6 and 5.2, there's not a significant difference. It's not, it's 1-ish%, a little bit more greater. It's not a lot. And so I would say that this is not a really nutrient dense food for calcium. There's not a big enough difference there. Okay, so yes, oranges are definitely nutrient dense in vitamin C. When we look at calcium, not so much. Okay, it's not rich in calcium. It still has some calcium. It's still definitely a good food choice, but not nutrient dense in calcium. Still definitely a good choice though. It does have calcium and it has a lot of vitamin C. So I would say yes, it's a good choice. Okay, let's compare two different types of drinks for nutrient density. All right, so in this table here, first of all, we're looking at percent contribution to adolescent female RDAs. The math has been done for us here. We're looking at a sugared soft drink, so not a diet soda, a soda, maybe a Coke, okay? So 8 ounces, which is 1 fluid cup, sugared soft drink on the left. Notice how we've got a list of some nutrients, right? Not all of them, but some of them. So protein, vitamin A, vitamin C, thiamine, thiamine, riboflavin, niacin. Those are all B vitamins, calcium and iron. Okay. This drink has none of those, but it does have calories. So look at the very top. It would meet, about 9% of this female's calorie need for the day. Okay. Nothing else. And then on the right-hand side, we've got a cup, same size, right? So we're doing a really equal comparison. These are both drinks, and it is the same amount of each drink, 1 cup or 8 fluid ounces. So it's a really good comparison. Yeah, it has calories, but it only has about, this looks like around, there's no numbers here, but around 4%. So it's definitely lower in calories. Look at the protein. She's going to meet, 18% of her protein needs for the day. Vitamin A, she's getting about 20%. Has some vitamin C, not a lot. I wouldn't call this a vitamin C rich food, but it's there. B vitamins, yeah, look at the riboflavin. Look at the calcium, okay? Some iron, some niacin. Okay, so I would say that this cup of fat-free milk is definitely more nutrient dense than this sugared soft drink, and it's definitely a much better choice. Lower in calories, higher in a lot of different nutrients. Okay, I want to introduce you to the term empty calorie foods. So this sugared soft drink would be a great example of an empty calorie food. It has calories, right? We're not showing sugar here, but it's high in sugar. We're also not showing fat. They could be high in fat. This probably isn't, but it definitely is high in sugar. and there's no other nutrients. So the nutrient value is crappy. Okay, what kinds of foods fall into this category? Sugared soft drinks, like the one shown here, chips, cookies, candy, fried foods, foods that, again, are not really providing any nutrition except for calories. Okay, so in general, empty calorie foods are not good choices. Okay, it brings us to nutrient density versus energy density. And so energy density, these are foods that are high in calories, but weigh very little. And a lot of times these are empty calorie foods, okay? Not always. So for example, energy dense foods, nuts, which are actually, in the right serving size, are very good for you, right? They're actually pretty high in nutrients, but they're also energy dense. So again, you have to pay attention to the serving size. You're only going to have a couple of ounces. If you're eating handfuls, that's not, you're getting a lot of calories. So again, energy dense, they have a lot of calories, but they weigh very little. Okay, a lot of calories and just a little bit of them. So nuts, and again, nuts are healthy in the right serving size. Cookies, fried foods, snack foods, those are other examples. Okay. It can help people, these types of foods can help people with poor appetite maintain or gain weight. Okay, so that's a positive. On the flip side, we've got low energy dense foods. Okay, they tend to contain a large amount of water and therefore fewer calories. They will weigh more because of that water. So examples of low energy dense foods are things like fruits, vegetables, stews, oatmeal. These types of foods can help keep calorie intake under control. You can eat a whole lot more of them for the same amount of calories than you can, for energy dense foods. With energy dense foods, you have to really watch the serving size because there's a lot of calories in just a very small amount. Another positive thing about low energy dense foods is that they can keep you feeling fuller longer. So they help with satiety. They keep you satiated. Remember, I introduced that term back in chapter 1. There it is again. This is a nice little graphic here showing calories. So here's some energy dense foods. Look, this is 400 calories of oil, and it's only taking up just this little tiny bit of the stomach. Here's 400 calories of, this looks like chicken wings, right? Or some type of deep fried chicken. Okay. And then that's compared to, look at this, 400 calories of vegetables. Okay. So again, you can see how it keeps you fuller longer. You can eat a whole lot more of them because you can eat a whole lot more for that same calorie count. Okay. So again, both have their value. Just be aware of them. So energy dense, high in calories, weigh very little. Low energy dense foods contain large amounts of water, weigh more, and have fewer calories. Okay, here's some examples of low versus medium versus high energy dense foods. Okay, so you can see low energy dense are things like lettuce, tomato, strawberries, broccoli, salsa, grapefruit, fat-free milk, fruits, vegetables. Those are very low. Then on low energy dense, you've got cottage cheese, beans, oatmeal, bananas, things like that. Medium energy density, ham, eggs, bagels, white bread. High energy density, graham crackers, chocolate chips, potato chips, bacon, peanuts, other nuts, vegetable oils. Okay, and energy dense does not mean bad. It just means you have to be aware of the serving size. You should always be aware of the serving size. Okay, last slide here, I believe. Just wanted to let you know that there are nutrient databases and tools, apps that you can use to help you to figure out calorie content, without having to do it all by hand. especially for foods that don't, have labels on them. Or if you're having serving sizes over or under the serving size on the package. You can use these these tools to figure out a food's energy density. It's determined by comparing foods, calorie count per gram of weight per food. Okay, so maybe you've heard of MyFitnessPal. That's an app that you can get, and there's also government, FDA, FDC.NAL.USDA, so government sponsored websites that are very accurate. And this infographic is it's a great picture to show you when you're eating foods that are higher energy density compared to foods that are lower energy density, kind of the amount of food that you can eat. So look, you've got a plate of fresh vegetables. This is probably a low fat dip. You've got a vegetable soup here, a salad. You can have a half of a cantaloupe. You can still have whole grains. So you got Cheerios and you've got something of a sandwich here. This is a lot of food for $15.75. Yeah, I guess that makes sense. Milk, juice, and I'm not sure what that drink is, but all of this food, this looks probably like a low-fat yogurt. You can have all of this food for 1,575 calories, right? Which if we're talking about the sedentary 40-year-old female who could only have 1,800, that's almost a whole day's worth of food. She can have a little bit more, compared to this. And so this is not a lot of food here in comparison, and it's the same calorie count. Okay, so again, foods that are higher in energy density compared to lower in energy density, and you can eat a whole lot more of low energy density foods, okay, for the same calories. Okay, so that is the end of the first part of this chapter. Please make sure to watch the video on Appendix J.